Hello, this is Jack Jackson. In this video, and we're going to start talking about similarity. So this playlist is going to be talking about mainly about similar triangles and a little more generally about similarity. Um, so we're going to talk about similar triangles, and this is going to be in Euclidean geometry. So first of all, what do we mean by a similar triangle? So here's a definition. Given a correspondence between triangle ABC and triangle A prime B prime C prime, we say that this is a similarity correspondence, and the two triangles are similar triangles. Specifically, triangle ABC is similar to triangle A prime B prime C prime, using this notation here with this little squiggle thing, tilde, representing the um, similarity. This happens if and only if all corresponding angles are congruent and the lengths of the corresponding sides are proportional. So what does that mean? Well, specifically it says triangle ABC is similar to triangle A prime B prime C prime if angle A is congruent to angle A prime, angle B is congruent to angle B prime, and angle C is congruent to angle C prime. All the corresponding interior angles, let's go ahead and just say that, are congruent. So that is exactly the same condition that we have for congruent triangles about the angles. But instead of the sides being necessarily um, congruent like they are in a congruence relation, we have sides lengths are proportional. So the distance from A prime to B prime divided by the distance from A to B is equal to the distance from B prime to C prime divided by the distance from B to C, and the distance from C prime to A prime divided by the distance to CA. All three of those ratios are some specific number K, which is constant, and it's for some positive real number constant. And that proportionality constant K is called the scale factor or dilation factor. This is related to the transformation called dilations, which we'll talk more about in our last unit. Now, let's think about some other geometries for just a very, very brief second. In hyperbolic and spherical geometries, you might recall that we have the angle, angle, angle condition, and that's sufficient to guarantee that the two triangles are congruent. So if you get just this first part here, that the three corresponding angles are congruent, then in fact, they have to be not only similar, but actually congruent, that A prime B prime equals AB and so forth. So there's really no such thing as similar triangles in hyperbolic and spherical geometries, at least that aren't congruent. So the topic of similar triangles is restricted by necessity to Euclidean geometry. Okay, so we're going to just do this in Euclidean geometry only. Now, the main condition that we're going to look at is, well, first of all, we should have some interesting question here, right? And here is our big question. It's very similar to the one that we asked when we were studying triangle congruence. Are there any sets of fewer than knowing all corresponding angles are congruent and all corresponding side lengths are proportional that results in the two triangles being similar? So if you remember, there were sets of three conditions. Let's see, what were they? Side, angle, side, 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 angle, 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 side. Those were enough in Euclidean geometry for congruence conditions that allowed us to say that the other three pieces were congruent as well. Can we have something kind of like that for similar triangles? That's kind of a big question. Well, one thing that should be fairly obvious to you is this. Because of the Euclidean angle sum for triangles, we know that the measures of the angles in any triangle always adds up to pi radians or 180 degrees. And since that is fixed, if we know that two corresponding pairs of angles are congruent, we know that we automatically get the third one congruent as well. So the AA condition really becomes the AAA condition almost automatically. So the real question is that enough to not only get the other angle congruent, but the sides proportional? So in other words, if we have this part here, where angle A is congruent to angle A prime and B is congruent to B prime, we can pretty quickly, using the angle sum theorem, get to angle C is congruent to angle C prime. But do we get this other part for uh, this proportionality thing? Okay, so let's look at that a little bit, and I'm going to use this GeoGebra workbook or GeoGebra activity here to explore this. Okay, so when this comes up, this is actually the same one that we looked at when we were exploring the angle triangle congruence possibility earlier. We found that it did not work. Okay, so let's start out here. Okay, and so here we have two triangles, triangle A, B, C1, and let's say here's A, B2, C2, and then we got A, B3, C3. Okay, and we can control the angle at A, that's the angle here, and we can control the second angle, which is at B. But notice that there are many places we could put this along here, and it does not change those angles. And here's a second set here. So we notice that these two triangles are not necessarily congruent. In fact, they're not congruent in this particular case. And that's because even though all of the corresponding angles are congruent, then the sides are clearly different lengths. Okay. Okay, and we can do this at any point along the way. So let's just kind of go through the steps again. Start with any angle there controlled by this first slider. It doesn't matter if it's an obtuse angle or acute angle. Then pick any point along here and pick the angle here. This has to go through the other side there. So now we know where the rest of where the point is there for C. There's your other angle. We know what it's going to have to be, and that makes a triangle. But this point can move, so we can get triangles of all different sizes. Specifically, here's a second or even a third triangle there. Let's just stop at 2. But if you look down here, what I have is I have the ratios of the sides. If you take the original A, which is this length here from B to C, and divide it by A2, which is this one up here, so that's 6.6 something divided by 13.93 something. You can see that here. Turns out to be about 0.47 something, almost 0.48. And if you do the same thing for this length B, the red length here from A to C, and put that one and divide it by A to B, C2, we get that. It always turns out to be the same ratio. Now the ratio may change as I change what this is, but the point is no matter where I put it, all three of these numbers are the same. So this is what we would call similar triangles. There's a third one here, different ratio, but at least all the same there for that one there. And it's not a fluke by the angle. Okay. And we have that. So that's kind of an interesting thing. So that's the first thing that we want to notice. Okay, so what we noticed about that, we noticed this earlier, and we're looking at seeing if angle or angle was enough to make the triangles congruent. We see that it's not enough in Euclidean geometry to have two or even three pairs of corresponding angles congruent. But there are infinitely many congruence classes, but that doesn't just mean anything will work. They're actually all in one similarity class. Okay, it's going to turn out that similarity of triangles is an equivalence relation, just like congruence of triangles is a similarity relation. And so we get similarity classes. So we see that we always get these here. Okay. Now, so it turns out that the angle triangle similarity theorem is the big result that we're going to use to help us prove two triangles are similar without having to go through and solve everything about them. And this turns out to be a very important thing. And from this, we're going to see if we can prove some other similarity results as well. So this is the most important foundational tool, and but it turns out to have a rather challenging proof here. So once again, here's our definition of a similar triangles, triangle ABC and triangle A prime B prime. We say that triangle ABC is similar to triangle A prime B prime C prime with that correspondence if and only if all corresponding angles are congruent, which is this, and ratios of the lengths of corresponding sides are proportional. So if we look at this, every length in the second triangle is this scale factor k times the corresponding length in the first triangle. So A prime B prime is k times AB, and B prime C prime is k times BC, and so forth. Now, if this scale factor turns out to be 1, then in fact all corresponding sides are congruent, and we have a congruence between the two triangles. Okay, so congruent triangles are definitely similar, but similar triangles are not necessarily congruent. So if that scale factor turns out to be between 0 and 1, then the second triangle is smaller than the first one. And if the factor is greater than 1, the second triangle will have longer corresponding lengths. It'll be bigger than the first one. So in each case, the measures of the corresponding angles are equal. So when you're an elementary school kid, you might have called these things the same shape but different size. So like the concept of congruence, we'll see that similarity of triangles is an equivalence relation. And here's an actual proof of that. And we're going to show that not only is similar triangles an equivalence relation, but we'll also show what the scale factor is. Okay. So here we go. Similarity of triangles is an equivalence relation. So we'll prove that. First thing is, given any triangle ABC, we know that each interior angle is congruent to itself, since congruence of angles is reflexive. We also know that the length of any side divided by itself is 1, so triangle ABC is congruent, or well, it's congruent to triangle ABC, but it's also similar to triangle ABC with a scale factor of 1. The similarity of triangles is a reflexive relation. Notice I didn't say triangles are reflexive, I said similarity of triangles is a reflexive relation. Now, so we've got reflexive. Remember, to show that it's equivalent relation has to be the relation has to be reflexive, symmetric, and transitive. So let's work on symmetric next. For symmetric, the hypothesis is you start with a pair of similar triangles like this. Now, by definition, all the corresponding, well, angle A is congruent to angle A prime, so A prime is congruent to angle A, since congruence of angles is a symmetric relation. And similarly, since you got angle B is congruent to B prime is congruent to B, and angle C is congruent to C prime, so angle C prime is congruent to C. Same reason. Now, by the definition of similar triangles, there exists some positive real constant so that these sides are proportional with that constant like this. K equals A prime B prime over AB, which is the same as B prime C prime over BC, which is the same as C prime A prime divided by CA. Now just take the reciprocal of both sides, or all four sides, I guess, and we get 1 over K is this. Well, if K is a positive constant, then 1 over K is also a positive constant, and sure enough, we've got proportional sides. So if triangle ABC is similar to triangle A prime B prime C prime with a scale factor of K, then when we reverse it, A prime B prime C prime triangle is similar to triangle ABC with the scale factor of 1 over K. So just think about it. If you're taking the lengths in the side AB, you're going to multiply by K to get A prime B prime. If you start with A prime B prime, you're going to divide by K to get back to or multiply by 1 over K to get back to the length AB. So therefore, similarity of triangles is a symmetric relation. All right, how about transitivity? Well, with transitivity, we are given a triangle ABC is similar to triangle A prime B prime C prime, let's say with the factor of J. And A prime B prime C prime is similar to A double prime B double prime C double prime. Let's say that one has a scale factor k. So by definition, angle A is congruent to angle A prime, and angle A prime is congruent to angle double prime. So angle A is congruent to angle A double prime, since congruence of angles is transitive. And the same way you get angle B congruent to angle B double prime and angle C congruent to C double prime. Now, by definitions of similar triangles, we get these two relationships. For the first similarity, scale factor of J, we get the length A prime to B prime over AB is equal to B prime C prime divided by BC, which is also equal to C prime A prime divided by CA, which is also what we're calling J. And we get a similar relationship for the next one, but with a factor of K. Now, all we're doing now is what happens if you multiply J and K. Well, you're multiplying this fraction here by the corresponding one here. See that right here? And do the same thing for the middle pair and the last pair, like this. Well, if you look, what happens is the A prime B primes cancel out, and you get A double prime B double prime over AB. And the same thing happens for the middle one and the last one. And that's exactly the fact that that is a constant is exactly what we mean by saying they're proportional. And what is that constant? Well, it's just the product of your two original proportionality constants, your two scale factors. So if triangle ABC is similar to triangle A prime B prime C prime with scale factor J, and triangle A prime B prime C prime is similar to triangle A double prime B double prime C double prime with scale factor K, then we get triangle ABC is similar to triangle A double prime B double prime C double prime with scale factor J times K. Therefore, similarity of triangles is a transitive relation. Since that relation is reflexive, symmetric, and transitive, by definition, the relation similarity of triangles is an equivalence relation. So that gives us similarity classes. Okay, like the concept of congruence, we will ultimately define a more general definition of similarity of any two geometric figures based on transformations, and will be some later sections of these notes studying on transformations, but for now we'll be using the definition above for similarity of triangles. And once again, because of the AAA triangle congruence theorem in spherical and hyperbolic geometries, there's no such thing as a non-congruent pair of similar triangles in these geometries, and we've seen that triangles in taxicab geometry have very different properties than triangles in Euclidean geometry. So the following study is kind of by necessity for Euclidean geometry only. Of course, that means that the Euclidean parallel postulate will be an important foundational part of the study, and perhaps the F and C and Z properties of the transversal to parallel lines theorem might be important as well. And just as we explore minimal sets of conditions that guarantee congruence of triangles, we will explore minimal sets of conditions that guarantee similarity of triangles. And the first set of conditions we'll explore is when we have two triangles with two pairs of corresponding congruent angles. Is this always enough to conclude that two triangles are similar? In other words, is this enough to guarantee that the remaining pair of angles are congruent and the lengths of corresponding sides are proportional? And here is our first exploration. And this one basically does what I just showed you in the sketch a little bit earlier. But here are the steps to do it if you want to do it yourself. In one single construction, construct an angle A and angle A prime so that angle A prime is congruent to the original angle A. They could be controlled by a slider or just controlled by controls on the angle A. Here I'm saying let's control it by a proper angle slider, or perhaps a proper angle slider slashed input box combination. Even better. Construct points B and B prime on one side of angle A and angle A prime respectively. Construct triangles ABC and triangle A prime B prime C prime, so that C and C prime are on opposite sides of angle A and angle A prime respectively, and angle B is congruent to angle B prime, with their common measurements controlled by a proper angle slider different from the one used to control the measure of angle A and measure of A prime. And again, we might as well say slider slash input box combination. Measure all the sides and angles of the triangles. Make a checkbox to hide and show these measurements. And here's our big question. Are these conditions sufficient to guarantee that these two triangles are, well, first of all, are they enough to make it congruent? And, I think you'll know the answer is no. Compute the following three ratios here and make a checkbox to hide and show those ratios. What do you notice about the ratios? Well, you should find that they are what? They're all the same. And so is the AA condition enough to guarantee similarity of triangles? And the answer should be yes. Okay. So from that, I encourage you to do that task yourself in GeoGebra. And you should have determined that the angle-angle condition is enough to determine that two triangles are similar, but not necessarily congruent. Now we're going to have to prove this, but once we prove it, we will establish the angle-angle triangle similarity condition. And here it states, given a pair of triangles with two pairs of corresponding congruent angles, the two triangles must be similar. Specifically, if we have triangle ABC and triangle A prime B prime C prime, with angle A congruent to angle A prime and angle B congruent to B prime, then triangle ABC is similar to triangle A prime B prime C prime. Turns out the proof of this result is one of the most challenging proofs that we're going to have to do this semester. We're going to actually end up using a few lemmas along the way. Along the way through this, we're going to end up using proof by induction, and then we're also going to even have to apply some limits. So the proof has more of a flavor of some other courses like analysis and some other things that are a little different than the kind of proofs that we would normally see in a geometry class. So we'll talk about the proofs of this over the course of the next few videos.